The graph of f prime, the derivative of f, is the line shown in the figure above. It says if f of 0 equals 5, then f of 1 equals blank. So this is actually a great question because it's a question that you should know how to do, hopefully, but it kind of approaches it in a different way, and so we have to kind of look at it. So this is a concept that you need to start thinking about, is that you're given a derivative, all right, so this is the graph of the derivative, and they're also giving you information about the original function, and they want to know something else about the original function. So whenever you see that pattern, whenever they're either giving you a graph of the derivative or a function of the derivative or whatever the case may be, if they're giving you the derivative, they give you information about the original function and they want to know something about the original function, whether or not it's the actual equation or whether or not it's, the function evaluated at a different value. Whenever that happens, we always want to make sure that we do solving differential equations. So remember, that's the one where you take a derivative and you find the integral of it, and then you use the initial condition. This is going to be our initial condition. So we can use our initial condition to say that, that's our new function, I guess you could say. Now, we have a couple options here. You could either determine what the equation of this line is and do it algebraically or using calculus, but I actually think it's a little bit easier in this case to do it geometrically and just find the area under the curve. So I'll show you both ways just so you have an idea, and you can kind of decide which way you like better, but you won't always necessarily, it won't always be easier to find the equation of the line, or you won't always know how to find the equation of the line. So sometimes you can't do that and you have to think about it in the way that it's geometric. So first let's do it the geometric way, since I think that's the easier way. Well, I lied. Let's do it the algebraic way, because that's the way that probably makes the most sense to you so far. So first of all, this is the function y equals, it looks like the y-intercept is 6, so I'm going to do plus 6, and then the slope, it looks like, is down 6 over 1, so negative 6. Alright, so that's negative 6x plus 6. So if I actually find the integral of that, so that's my equation, if I actually find the integral of that in order to find the original function, I get negative 6x squared over 2 plus 6x plus c. So if I simplify that, that's negative 3x squared plus 6x plus c. And again, I want to find out what c is, so I'm going to use this initial condition and actually figure out what c is. So if I plug in 5 for y and I plug in 0 for x, I get that c is 5. Alright, so from there, I'm going to just kind of edit this equation up here. So I'm just going to erase that and put a 5. Alright, and then if I want to actually evaluate, so now I want to know what f of 1 is. So if I actually plug 1 into this function, what does it equal, essentially? So y equals negative 3 times 1 plus 6 times 1 plus 5. So that would be negative 3 plus 6 plus 5, or in other words, 3 plus 5, which is 8. Alright, so that's the algebraic way of doing it. That's the way that we've done it most often in class. We're given a derivative, we find the integral of it so that we can know the original function. We use the initial condition to figure out what c is, and we plug in the new value to evaluate the function. That's fine. However, again, like I said, sometimes you're not able to take the integral. Maybe you don't know what the function is, or maybe it's too difficult to take the integral. If that is the case, here's the geometric way of doing it. So keep in mind that this is the way we would do it algebraically. We have 8 as our answer. Let me go ahead and erase all of that so that we can look at it the geometric way. So geometrically, remember that the integral is just the area under the curve. So if I'm going to try and find the integral of this, since this is the derivative, I'm looking for the area under that curve. And since it's a triangle, it should be pretty easy to find the area. I have a base of 1, a height of 6, and I divide that by 2. So 1 times 6 is 6, divided by 2 is 3. So this has an area of 3. So here's what this means. At 0, and so here's kind of how to interpret it in calculus. And this is actually a huge concept, so make sure you guys are following along with this. This initial condition tells me that at 0, the function equals 5. So there's actually a literal point at 0, 5. Alright, over here at x equals 1, okay, which is my new value that I'm trying to find, because this is the derivative, this is the graph of the derivative, and I just found that the area under the curve was 3, what that literally means, in translation over to here, what that literally means is that if I started at 0 and my function actually equaled 5, from 0 to 1, the area under the curve is 3. That literally means that I accumulated 3 more units, positive 3 more units past what I was at 0. So from 0 to 1, I accumulated 3 units. So what that means is if I started at 5 and I accumulated 3, I'm actually going up 3 more. 1, 2, 3. So my new point would be at 1, 8. Alright, so do you guys see the relationship between those? Here's the initial condition they gave us, f of 0 equals 5. I found the area under the curve to be 3 units. I literally accumulated 3 units. So from 0 to 1, I went up by 3. And that's how I got to 8 there. So the answer is D, 8. And those are 2 ways of doing it, but again, it's very important to know that second way because sometimes you won't be able to find the integral. Obviously, it was so much easier to do it this way than to do it the other way. Or sometimes they'll just give you what the area is. Like they'll say the area under this curve is 20, here's an initial condition, what's f of whatever. Okay, so it's very important to understand this way as well.